The third and final application is about water pumps. So this is a pretty cool one and definitely a step up from the previous two. So let's think about this example. We'll just dive right in. The tank below, you see it right there, is filled with water. Now that's a pretty big tank. It's a cylinder with a radius of 2 meters and a height of 3 meters. Ignore the scaling there. Pretty big tank of water. Find the work to pump all of the water out of the top of that tank. So all the water's got to get up and out, and you can imagine, well, at first, the water at the top of the tank's going to come out very easily, but the water toward the middle or the bottom of the tank has a long way to go in order to get pumped all the way out. And then we're told a couple of nice, constants here. The density of water is 1,000 kilograms per meter cubed. And acceleration due to gravity is 9.8 meters per second squared. I will always provide these sort of constants in any problem that you are given on a quiz or a test, which might not be the case when you take your physics courses. They might expect you to remember these. I do not. We're just focused on the math, which is hard enough. Okay, so we've got this big tank of water. Where are we even going to begin trying to figure out the amount of work it takes to get all the water out of that thing? For one, I'm going to redraw this with an x-axis, so very similar to the way that we did with the hanging chain or rope. So we're going to say, I've got the cylinder drawn there, and I set up my x-axis saying 0 is at the top, and it's going positive as I go downwards, and so the bottom of that cylinder is at 3 meters right there. Okay. And then you notice that I've drawn just like a random layer of water. So the way we're going to think of this, we're going to add up all of the work. Let me start again. So we're going to think of how much work would it take to get rid of a single layer. And then we're going to go and integrate from 0 to 3, and that will add up all of the work for every single one of the infinitely many layers of water in this tank. So we'll approach this by thinking, okay, how much work to get rid of to pump out just a single layer, an infinitely thin little layer of water. And then once we know that, then we can integrate it from 0 to 3, and that will add up all those infinitely many layers of water. Okay, so I've drawn an infinitely thin little layer of water, and I've noted that it has a distance of x to get up and out of the top. How far does that have to go to get out? X, and that comes from the way I set up my axis, right? Wherever this is located, well, that's how far it has to go to get out. So if I'm closer to the top, it has a very small distance. If I'm closer to the bottom, it's got a distance of maybe almost 3 or 3 for the very last layer to get out. And I've noted the radius of my cylinder there is 2. And I've noted the infinitesimal thickness of my little layer of water as delta x, or the change in x. That will represent the tiny little infinitesimal thickness. Okay, so it turns out it's going to take quite a bit of thought to figure out how much work it takes to just get a single layer, some random layer of water out the top. But once we have that, then it'll be pretty fast to set up the integral and get the answer. Okay, so kind of buckle your seatbelts. You might be here for a little bit. Let's figure out the work to pump out some layer of water. Well, if we go back to our formulas, remember that work equals mass times acceleration times distance. Here our units are in metric, right? Meters. Okay, mass times acceleration times distance. If we look closer at mass mass is density times volume. Let's make sense of that. So if you have the amount of volume of some fluid or some substance, multiply it by its density, that's how massive it is. Hopefully that makes sense to you. So if something is very, very heavy for its size, it's very dense, well, it's got more mass than something that is less dense, even though it might be the same volume. So we're going to use some familiar looking variables there. We're going to say m equals rho times capital V. Mass equals density. We use the rho. We've seen that. And volume is capital V. Okay, so put it all together, and work equals rho times V times A times D. Density times volume times acceleration times distance. Okay. Now we got something to work with. If we can figure out what each of these are for some layer of water, then we're in business. So it turns out the density is no problem. That's the 1,000 kilograms per meter cubed. Turns out acceleration, no problem. That's the 9.8 meters per second squared. The distance, well, that's no problem. It's got to go a distance of x. The hard part is figuring out the volume of that little layer of water. Actually, in this problem, the volume's not even that bad, although the other numbers we have immediately, the volume, we've got to do a little bit more thought. Okay, so here it comes. I'm going to try and keep everything on the screen. I think it just barely fits. Okay, so the density is the 1,000 kilograms per meter cubed. The volume, okay, so think about the volume of a little infinitely thin little layer. Okay, well, that would be the area times the thickness. So the area, well, that's the area of a circle. So that's pi r squared, and we know the radius is 2. So that's pi times 2 squared. There's the area. But we got to multiply that by the little bit of thickness that we see there, and that's what we're calling delta x. So that guy right there is the volume. Pi r squared times delta x, the area times the thickness. And then the acceleration due to gravity, there's where the 9.8 comes in. And the distance that this layer must travel to get up and out of the top of the tank is x. So it's got to move an x units, x meters to get up and out. Let's simplify that a little bit, and now I'm definitely going to have to slide this down. 9.8 times 4 times 1,000 would give us 39,200, and then we'll just leave the pi for now. And here we can maybe put the x right there, and then the delta x on the end. Okay. Let me leave that for us. Once we have the work to pump out some layer of water, then it will be very easy to find the sum of the work of all of the infinitely many layers. All we got to do is integrate. So if we were to add up all of the infinitely many layers and how much work it takes to get them all, we'll say, all right, take our result right there and integrate it over the distance 0 to 3. And one important feature that happens is the delta x, now we write as dx, the infinitesimal, or you might say the differential of x. It's as if that thickness shrinks down to infinitely thin officially at this point. Okay, but all right, I think you get it, right? We take that, we integrate it, right? Delta x becomes dx, but okay, everything else is the same. You might notice that the 39,200 pi is a constant. You could pull that out if you really want. And wow, okay, we're integrating x. Like that's nice after all of this work setting it up, that our integral is simply an x. All right, so that's 19,600 pi x squared from 0 to 3. And we can get our final answer right here. We'll plug the 3 in, right? and get 176,400 pi. And remember, for metric, your work is joules. Perhaps you prefer to multiply that pi in there. Here's the answer for that. 554,176.9 joules. I rounded to one decimal place. Either answer is okay. Okay, so I've got one more example of water pumps, and this one's gonna give us a bit of a harder time. Let's see here. Okay, I'll just show you all this. All right. Take a moment to copy this and the drawing. I'll go ahead and read it. Find the work to pump the water out of the top of this tank. The water level is 1 foot below the top, and the density of water is 62.5 pounds per foot cubed. So you notice this is, they're calling it a tank, but I'd say this is really like a trough. A very big trough. You notice that it's 10 feet tall, it's 20 feet long, and at the top it's 8 feet wide. But we've got these triangles on either end, and then it's got a length of 20 feet. So this is they have these just massive tanks in these problems, I guess, to keep the numbers relatively nice. And we're dealing with feet, right? So we've got the English system. It's good to see both styles. Also, what makes this problem a big step up from the previous problem, right? So the previous problem, our tank was a cylinder. So it turned out the volume of any given layer in that cylinder is always the same. It was always, well, I write pi times 2 squared times delta x was the volume of some layer. In this case, with this tank, the volume of any given layer of water changes. So, at the top, it's like that big rectangle that you see is like the very first layer. But as we go down, we get these smaller, thinner rectangles. So the volume of water of each layer changes. And that's going to take some thought. Okay. But it's basically the same approach. Here's how we're going to start. We're going to think about just our formula here. And it's a little bit different when it comes to doing this in the English units or the standard units. So the work for some layer, well, work equals force times distance. And we prefer to think of it as force times distance because pounds are already a force. They already have acceleration embedded in the number. So what we're going to do is think, okay, well then force, we don't have to worry about acceleration. Force is density times volume. Okay. And then the distance there as well. So same formula as before, but now we don't have to think about the 9.8 meters per second squared for gravity, right? Because that's already taken into account in the density, because they gave the density in pounds per cubic foot. Okay. So now that we've got our formula straight, let's think about the volume to pump out some given layer of water. Let's see how this goes. Here's what I'm going to do. I'm going to draw, maybe look at just this first. Okay, that's good enough. Think of just the very end of that trough or that tank, right? It's that triangle. And here's how I recommend you set up an XY plane. So it turns out we can't get away with just an x-axis going down in this case. We need a y-axis as well, because this is some random layer of water in the middle. Because that's going to change, right? It depends on the x value, and then the y value there. That length is important as well, because that changes depending on where your x is. So we need an x and y coordinate system here. Draw the X coming straight through the middle of that trough, cutting it in half, and still make X going positive in the downward direction. Then think of Y as going positive in this direction. So what would that mean? Well, the trough is 10 feet tall, right? So that would be X equals 10. And the trough is 8 feet wide at the top. So that would make, if that's 0, that would make this 4 and negative 4, so it's 8 feet wide, right? So we got the 4 there on the Y. Now notice there's some symmetry. Actually, before we go on, what is that line there again? That is the volume, or like that's a layer of water, I guess is what I'm trying to draw. So that could be anywhere, but that's just some layer of water inside the tank. Okay, now notice there's some symmetry here, right? The left and the right side are the same size. So we can simplify this just a bit and only draw half of it. So I've still got my X and my Y axes, still saying that's 10 and that's 4, but now I'm only considering half. And there's the layer of water, or we should say that's half of the layer of water, right, corresponding to this. So when that tank, kind of tapers down, or it's not a perfectly, like it's right, it changes, thickness, as it moves up against gravity. Highly recommend draw just the end of the tank, set it up on an XY plane somehow to start to get your function or figure out the volume of the amount of water for any given layer. Okay, moving ahead. Here is, I'll just show you all this. If we can find the length of the layer, so when I say the length of the layer, I'm really talking about this full length here, the length of that water. Then we will know the volume of water equals twice that length. Okay, I should say if we can find the length of the layer here. My mistake. If we can figure out this length, then the volume will be 2 times that, because it's actually twice as long, times 20 times delta x. Where do these other parts come from? So maybe twice the length makes sense because we got to double it. But where does that times 20 come in? So remember that we're just looking at the very end of the tank. The tank is 20 feet long. So, we're just looking here. So if we can figure out that length, well, then we got to multiply it by 20 to get the full area of that rectangle. And then we got to multiply it by delta x. Delta x is the thickness of our layer, and we're thinking of it as infinitesimal. Okay, so this is really like length times width times height or something, right, to get the volume. So you notice that if we can get that length, this length right here, then we got the volume. And if we got the volume, then we can figure out the work for the layer. If we can figure out the work for the layer, then we can integrate, and we got this thing. Gotta break it down. Okay, so what is the length right there in terms of x? Right, that's the question. Turns out what we need to know is the equation of the line, and the line I'm referring to is this line right here. That's slicing down through. The equation of the line that defines that the slope of, the edge of that tank. Slope is an aspect of it. I shouldn't say it's as simple as the slope. You get the idea. What's the equation of that line? Okay, well, we need 2 things for the equation of a line. We need the slope and the y-intercept. And those aren't going to be too hard to figure out. Okay, if you look at that equation, or look at that line, that picture, what's the slope of that line? And now it's kind of funky because we've changed the x and the y axes. But you think, well, you know, if I thought of it in the traditional way, right, like rise over run, the y is the rise, so it drops 4 and then it runs 10. Y decreases by 4 and then x increases by 10. So negative 4 over 10, which would be negative 2 over 5. Or, if you wanted to, and I've got my drawing here, I usually can't do this on a whiteboard. What we could do is take our drawing and, put it in the more traditional style, right? So the y and the x. And yep, I see it there. It drops 4, it runs 10. Negative 4 over 10 is the slope. So here you go. Y equals negative 4 over 10, or negative 2 fifths x plus, and what's the y-intercept of that line? Well, it's 4, where it passes through the y-axis. Negative 2 fifths x plus 4. So that's what we can put right there. Volume equals 2 times negative 2 fifths x plus 4 times 20 times delta x. Let's simplify that. Volume equals, and I just distributed the 2 and the 20 in here, negative 16x plus 160 delta x. So really what's going on, that negative 16x plus 160, that describes the area of the rectangle of any given layer, and then the little bit of thickness to get the volume. Okay. Moving on. Once we've got the volume of some layer, we want to write the work to remove or pump out that layer. So remember that work equals density times volume times distance. So there's the density of the water, 62.5 pounds per cubic foot, times the volume that we just found, times the distance. Well, how far does any given layer need to be removed from the tank? X. Now, perhaps, you don't like the way I've gone about this so far. Maybe you don't like the way I set up my XY plane, like reversed. But I highly recommend you do it. Why? Because how far does any given layer need to go to get out of the tank? It's always x, right? How far is that distance? It's x. X to get out of the tank. And we see that here. The distance is x. I don't know if that wins you over to doing it this way. You can set it up other ways. It's not the coordinate system that is the magic, and gets you the right answer. You can change your coordinate system, but some ways are more difficult than others. Okay, so here we go. We've got the work to remove some layer. So what is the sum of all the work for all the layers? Well, we got to take that and integrate. Notice the 62.5 is a constant, so that's out front. The integral is from 1 to 10. Why is the integral from 1 to 10? I keep having to pull back previous pages. Because in the original problem, it said the water level is 1 foot below the top. So it's 10 feet down here. It's only 1 foot. It's 1 foot deep there. We're not going all the way to 0. So we integrate from 1 foot deep to 10 feet deep. From 1 to 10. And then we just continue. We've got our volume there, negative 16x plus 160. I put the x kind of shifted positions, and then the delta x becomes dx. Okay. And there we are. From there, well, not too hard to get this, right? Distribute your x and integrate 62.5 times the quantity negative 16 over 3 x to the third plus 80x squared from 1 to 10. And I'm just going to go ahead and tell you the final answer. Plug in your 10, plug in your 1, and you'll get 161,740.8 foot-pounds. The numbers we get and the problems in this section are huge because we're dealing with these massive objects and tanks and chains and everything else. Okay. There you go. That is the end of our section and the end of our applications, our more applications of integrals. Good luck in the homework. See you in office hours.